Thanks. It's great to be here. So today I'm going to be talking about cross-validation. So cross-validation is pretty ubiquitous in data analysis. We all use it. But if we have modern large data problems, cross-validation is actually often far too expensive to run in practice. And so today I'll be talking about an approximation to cross-validation and theory and experiments to support that. Okay, so I think the story not just of this decade, but probably the last like 4 or 5 decades has been that as we get better computation, practitioners are able to run increasingly complex data analysis methods. In some sense, our goal is to use all of this data analysis in life-changing application areas, areas like medicine or cybersecurity or personal finance. And so if we're using our methods in these areas where it's really going to affect people's lives, I think a really big question that we want to be asking is, do our methods work? Now, I think there are 2 complementary approaches to answering this question. One is to say, hey, before I run any data analysis, I know that it's going to have theoretical guarantees in advance. And for some of you who are at my seminar, you know that I think that's a really interesting area and one worthy of study. But something that we have to worry about in these cases is that people are running these algorithms because we can run the algorithm right away, but it might take a long time to develop that statistical theory. And when we think about the time that users are taking, you know, we care about not just running time, but user time. That's still time before we can check if something's working, and they could be running it willy-nilly, and maybe it actually performs pretty poorly. And so another very complementary approach that we could take, and one that I think that we all take without even thinking about it, is we could just evaluate after inference. Now, sort of a very common way to do this is cross-validation. And not just cross-validation, but things like the jackknife, things like the bootstrap. The reason that we like these so much is that you can run them on basically anything. They're completely agnostic to model. You can run them, and you don't have to sort of think about it a lot beforehand. You can just immediately get an answer. Okay, so what's the problem? Well, one big problem is that if we want something like, for instance, leave one out cross-validation, well, that requires running whatever our method is n times for n data points. And so if we already have an algorithm that's at least linear in the size of the data, which is, I think, a big reason that we have workshops like the current one to think about, gosh, you know, how do we scale our algorithms, our individual algorithms down? Well, if we have one that's already at linear in the size of the data, this is going to make it quadratic. In general, it's going to sort of drastically increase the cost of our algorithm in a way that we definitely are not comfortable with. And this is true for other types of cross-validation as well, maybe not so drastic or maybe even more drastic. Okay, and so what I'm going to look at today is how we can have a nice approximation to cross-validation. One that's going to be fast, that's going to be automatic. So again, we want to care about user time. We want something that's going to work very generally, that people don't have to sort of derive equations to make it work. It's just going to work out in the end. And that's high quality. So it has theory to support it, and it also has experiments to support it. And the particular approximation that we're going to be looking at today is very simple in some sense. It's just a Taylor expansion and a dimensionality reduction. And we're just going to require one run of the algorithm in the end, not n runs, not many, many runs. Okay, so going forward, what I'm going to do is I'm just going to review what do we mean by cross-validation, what are we trying to accomplish in cross-validation, and some other things beyond cross-validation, like, again, jackknife and bootstrap. Then I'll talk about an approximation that helps us deal with this large data problem, where we have tons of data, n is very large. And then an approximation for dealing with the high dimension problem, because these often go hand in hand. Right? Okay, so first let's start by talking about cross-validation. So we're doing some data analysis, and out in the world there are some parameters, let's call them theta. They're unknowns that we are interested in. And we imagine that we have something like a loss for each of our data points that depends on theta. So let's call it f sub n for the nth data point. And typically we'll collect capital N data points, so we'll have sort of the loss over all of these data. And then the way that we might estimate theta is we'll minimize that loss. And something that you might often typically do in this K2 is maybe include some kind of regularizing term and minimize over the whole thing. Now, many familiar problems look like this. So for instance, if I'm doing maximum likelihood estimation, then each of these losses is a negative log likelihood for each data point. More generally, M estimation fits into this framework. Obviously, loss minimization and regularization. You can even think of maximum a posteriori within this framework, because you can think of the regularizer as something like the prime. Okay, so to see how we might evaluate our theta hat after this. Let's look at just one example first. Let's look at leave one out cross-validation to be concrete. So the way that leave one out cross-validation, or sometimes abbreviated LOOCV, works is we have a bunch of our data to start with. And so for the purposes of this cartoon, we have 6 data points. They're the little boxes. And normally, we would run our data analysis over the full data. But again, we want to actually evaluate it and see what it might look like on if we had some totally new data. And so the idea of leave one out cross-validation is we leave one out. We leave one data point out. So in particular, we treat all of the remaining data points as our training data. And we treat that one data point we left out as the test data. And now we take just the training data points and we calculate an estimate of theta hat just for the training data points. So that's what this superscript 1 is suggesting, is that this is after we've left out data point 1, this is the theta hat that we calculate on what remains. And then we might do something with this theta hat, like we might predict on that one remaining test data point, or we might just keep it around if we're doing jackknife. There are many options. But the first thing we do is we calculate this theta hat. OK, and now we do this when we leave out the second data point. We do the same thing, only now we calculate theta hat having left out the second data point, and maybe we do something with that. And we keep doing this up until the nth data point, where we calculate theta hat n. And so just to establish maybe exactly what we're doing here is we're solving the exact same problem as the original data analysis problem. We've just slightly changed the weights. That is, every data point in the first data analysis problem had a weight of size 1. And now we're saying that almost every data point has a weight of size 1. It's just whatever data point we're leaving out has a weight of size 0. OK, so that's leave one out cross-validation. And the thing that we can sort of immediately see now is that there's a very big time cost associated with leave one out cross-validation. That whatever it takes to compute theta hat, which in general could be very complex and very expensive, now is going to take, if we do each one of these leave one out cross-validation runs, is going to take n times that cost. And again, so a linear problem becomes quadratic now. A quadratic problem becomes cubic. Things get much worse computationally as a result. Now, this sort of framework isn't specific to leave one out cross-validation. We can think of a more general type of cross-validation, in which case we just change the weights. Instead of saying, hey, we only have a 1 for everything except for the point we leave out, we'll have more general weights. So for instance, in leave k out cross-validation, everything is 1 except for the k points we leave out. And we leave out every combination of k points. Or you could have k-fold cross-validation. Or in fact, it doesn't even have to be cross-validation. You could have jackknife or bootstrap. Those all fit into the framework that I'm describing right now, this weighting framework. And now when we think about going beyond cross-validation, so it's not just leave one out now, it's cross-validation in general, it's jackknife, and so on, we still have the same time cost issue. And maybe it's not exactly n. It could be better or worse, but it's still many times the cost of a single data analysis. And if you are dealing with this in practice, you really only want to run your data analysis once, not many times. And so that's what we're going to be aiming for. How can we just run our data analysis once? Now, the high-level idea that we're going to be taking advantage of here is that, hey, all these weightings, sort of by design, they're meant to look kind of like the original problem. And so in some sense, you could think of us as having perturbed away from our weights of all size 1 to a slightly different set of weights. And so how about instead of changing those weights and then completely rerunning our analysis, we just do a Taylor expansion. So that's exactly what our approximation is going to be. So this is the exact thing. We want to calculate this for every weight that we might have in leave one out cross-validation, or if we're doing k-fold cross-validation, every weight that we might have for k-fold cross-validation. And our approximation, to describe it, I'll first introduce a little notation. So first of all, for this part of our objective, we'll call that capital F. And now in order to take a Taylor expansion, we're going to have to take some derivatives. And so the first thing that I'll define, again, just for notation, is the Hessian of the objective. This is just the matrix of second derivatives of the objective, just defining some notation. And so finally, the approximation is literally just a Taylor expansion around a single run of this algorithm. OK, so a couple of points. So this is a first-order Taylor expansion around W. And the way that we're thinking about using this is not just putting in a change in W here, but in particular a change in W relative to 1, because that's the case where we have weight of size 1 for each data point. That's the original data analysis algorithm. OK, something to note here is this requires 2 times differentiability. So technically speaking, we do have more requirements than just running cross-validation out of the box. So in particular, you see this twice differentiability comes up in calculating the Hessian, which we then use in this evaluation of our approximation. And so this precludes using things like, for instance, a regularizer that would be very common that you might want to use is L1 regularization. It's not twice differentiable. I'll come back to this later, but at this moment, it sounds like we can't do that. So this is a limitation. It's not a huge limitation, but it's a limitation. Okay. Now, something that traditionally, back in the day, somebody might have said is, oh gosh, well, there's a lot of derivatives here. And so that sounds like the practitioner is going to have to sit down and like derive some derivatives, and that's just not the case anymore. So thankfully, we have modern automatic differentiation tools. And so this is something that we can be used very automatically, and that nobody has to write down equations. So I want to make sure we're all on the same page. I'm talking about automatic differentiation, not numerical differentiation or symbolic differentiation. If you're not familiar with automatic differentiation, I really want to strongly recommend this Baden et al. Reference that I have here, which is a great review of modern automatic differentiation methods, which I think have really revolutionized statistics and machine learning in the past few years. Okay, so this idea of a first-order Taylor expansion is actually an idea that dates back to like 1972. It was a great idea then, it's a great idea now. But it was used for very different purposes then. So for one thing, in 1972, nobody was using automatic differentiation in the statistics literature, and so this was not considered to be a practical thing that anybody would use in practice because you'd have to derive too many derivatives. On top of that, a number of assumptions were made in part because the whole point of this infinitesimal jackknife, like a jackknife where you take an epsilon down to 0, was to prove things about consistency. And that's just a totally different direction than what we're thinking about here. Here, we don't necessarily want to assume that an infinite population might even exist. We're very concerned about the data we have and how well our algorithm performs on that data. And so we can make very different assumptions, and in fact, those assumptions are much more realistic than the assumptions that would have been made in 1972 for our particular problem. Okay, also, I want to point to a number of works in the machine learning literature recently that have made other linear approximations. But again, their assumptions are quite strong relative to ours. So in particular, they assume things that preclude basically even very simple distributions, like a Gaussian distribution, which certainly we want our theory to apply to. Or they look just at Gaussians. And again, we want our theory to apply much, much more generally. And that's what we have here. Okay, so again, let's take a look at cost. So if I did basic leave one out cross-validation, we said already that's n times the cost of a single data analysis. Whereas if we look at the cost of our approximation here, which you'll notice we denote as ij for infinitesimal jackknife in our notation, the cost is now you run one data analysis to get theta hat. That's just the original data analysis. So you only have to run it once. And then you do n matrix vector multiplications. And so instead of having a factor of n, we add n. So something that was already linear stays linear. It's a huge difference. And we're going to see this in our theory and our practice. Okay, so first, a little theory. So we have a very general theorem that I'm not going to go into a lot of detail on because I think it's going to be pretty impenetrable for such a short talk, that says that under various conditions and various weighting schemes, so again, this would be like leave one out cross-validation, k-fold cross-validation, bootstrap, et cetera, we can bound the worst case error between our approximation and the exact leave one out cross-validation. So worst case means over all the different runs within leave one out cross-validation, what is the worst, the farthest we are off. Now I think what's more easy to take in is corollaries of our theorem. So here let me just talk about the corollary for leave k out CV. What does our theorem imply about leave k out cross-validation? So leave k out cross-validation is the case now where our weighting scheme is such that we consider all weights where every one of our weights is 1 except for k of the weights. So we consider every possible weight vector that looks like that. And we can show that the maximum error over every one of those weight vectors is bounded. If our derivatives, if our gradients are bounded, which is often not the case as n goes to infinity, but I'll mention it. If that's true, then we have a bound that looks like n to the negative 2. If, I think much more realistically, our gradients are not bounded, then we have a bound that looks like n to the negative 1. Okay, so that looks good in theory, but what does it look like in practice? So let's see some plots. So for our experiments, first I'm going to look at simulated data, and then I'm going to look at real data. So first, for the simulated data, we're simulating from a logistic regression model. What you're seeing on the x-axis is trial number. We run 50 different trials of this. So simulated is nice because we can make as much data as we want. Then on the y-axis, we have the difference from the test set error. So you can think of cross-validation as often doing something like estimating test set error. And so that's what we're going to compare to. And so in red here, we have exact cross-validation. And you see that it's sort of around the test set error. In green, we have our approximate cross-validation. And the key thing is that it's close to exact cross-validation. In blue, we have the training error. Now, a totally reasonable thing that you might have thought is, hey, why don't I just train on all of my data and test on all of my data? And I think we all know that that will tend to be biased. In particular, that will tend to underestimate the error. And that's what we're seeing here. OK, so the next thing we do is we look at simulated data from Poisson regression. Now, I think that something that I tend to forget, and this plot reminds me, is that cross-validation is not always that great. And so in this particular case, we see that cross-validation sometimes really sort of messes up an estimating test set error. But we're not aiming for test set error here. We're aiming for an approximation of cross-validation because that's what people are using in practice because it's so easy to use. And we see that our approximate cross-validation is giving a good approximation for that. And finally, we get training error, which is even worse, just much worse in this problem, and that's in blue. And again, it's underestimating error. OK, it's not just error. It's not just quality. It's also time. And so here we have a log-log plot as we increase the size of our data set. How does time behave? And again, we see that our method is, in this case, about an order of magnitude faster than exact cross-validation. Also note that in some sense, a lot of our experiments here are necessarily on the order of tens of thousands of data points or lower just because we wanted to compare to cross-validation. To get beyond that, it's difficult to actually even run cross-validation, whereas you can run our method much beyond that. OK, let's look at a real data set. So here we have a two-stage analysis of mice gene expression data, where we first use a spline smoother with different degrees of freedom and then cluster the resulting splines. This is something where it would be very challenging, and you'd sort of have to do it for every new approach to develop a bunch of statistical theory for and to work out exactly what's happening and have something that works specifically for this case, whereas it's very easy to run cross-validation. OK, so what we see in this plot is, remember, so we're looking at leave one out cross-validation. For every point we leave out, we get a theta hat estimate. That's our infinitesimal jackknife estimate. And we would get the real cross-validation that we could compare to. And so that's what we're comparing to here. We're saying for each point we leave out, there's a little dot for the CV prediction error on the x-axis and for the infinitesimal jackknife prediction error on the y-axis. Now, it's hard to take sort of 1,000 data points and see what the trend is. And so what we've also done is plot the contours of sort of the resulting density. And we see that they agree very well with x equals y, which is what we're aiming for. That means that the infinitesimal jackknife agrees with leave one out cross-validation. And as I said, this is actually over a number of degrees of freedom. You might use cross-validation here to choose the degrees of freedom. And so we see a similar plot for each degree of freedom in this problem. What about time? So here, I just want to be really clear. When we talk about timing of our approximation, I'm separating that from the cost of the original algorithm. So here, we first have the cost of the original algorithm across degrees of freedom. That's learning ones. Then we have the timing of our approximation after you ran that original algorithm. That's infinitesimal jackknife. And also, we have the timing of exact cross-validation after you ran that original algorithm. And again, you see that our algorithm, our approximation, takes about the same amount of time as learning once, whereas exact cross-validation takes at least an order of magnitude longer. And here you're getting a full approximation to leave one out, as opposed to just twofold cross-validation, which would cost the same amount of time, but probably be more biased, much more biased, in fact. OK, so that all sounds really good. We have this nice general thing that we want to do, things like leave one out cross-validation, more general types of cross-validation. We have this approximation now, which is this Taylor series approximation. And a point that I want to make is something you should be concerned about is this matrix inverse. Whenever you see a matrix inverse, I think you should get a little bit worried in life. So in particular, when I talked about the cost earlier, I did tell you accurately the cost in terms of the number of data points. I didn't tell you the cost in terms of the dimension of the problem. So in particular, this matrix, this H matrix, is d by d, where d is the dimension of theta. And so if I take a matrix inverse of size d, well, that's going to be a d cubed cost, about d cubed. And then the matrix multiplies are actually n times d squared. And so if d is approaching n, this is actually pretty expensive. And in sort of very modern high dimension problems, this is a real concern. And in fact, I think that in many cases, if you had extremely small dimension and giant data, trading error would be okay. And so these are the cases in some sense where you really, really want cross-validation. Okay, so in this case, what can we do? Well, it turns out, by the way, before I say what can we do, I'll say that it's actually even worse than this. So it's not just, oh, this is really expensive, but it would be great if we can run it. The accuracy is also not great in high dimensions. So in particular, first look at the blue line here. So what we have on the x-axis is log of the number of data points, and what we have on the y-axis is log of the error. And so we expected from our theory before to have a slope that as we increase the number of data points, it should be a slope that's sort of less than -1, that's, goes faster than -1. And in fact, that's what we see. In fact, it looks like -2, which is great. That's a great slope. It seems like we're getting a lot less error as we get more data points. But if we so in that case, we let the dimension be constant. If we let the dimension actually grow with n, if we let it be n over 10, as in the red line, and we see that the error is not decreasing. In fact, it might even be increasing slightly. And so in fact, this really hurts accuracy as well as computational cost. And this isn't an issue that's just going to go away on its own. So something that I think you all might have talked about yesterday in the tutorials is this notion of an effective dimension, a much smaller dimension. It's actually a notion that just came up in the last talk. This notion of a much smaller dimension that things really exist in. What if our theta parameter actually only has a very few non-zero values and everything else is 0? Well, the problem is, even if we assume that this problem doesn't go away, it turns out to create this plot, we assumed that the effective dimension was just 2. And we just had zeros for every other value of theta, every other dimension in theta, and we still got this behavior. So we have to actively use dimensionality reduction. It won't just come to us for free. Okay, so that's what we do next. So now what we're going to say is, let's reduce dimensionality. Hey, a great way to do that would be lasso, to use an L1 penalty. This is something that a lot of people use for dimensionality reduction. And remember, we just said we can't use that with infinitesimal jackknife because it's not twice differentiable. That penalty isn't twice differentiable. Okay, what are we going to do? Well, a number of authors have proposed using smooth approximations to the L1 penalty. So they are twice differentiable. And they have some approximation quantity eta that tells you how smooth it is. A problem is that we're going to show that these perform poorly. So we can't just use them on their own. I'll show that in a few slides. Okay, so what we're going to do instead is another idea that's proposed by these authors is take the amount of smoothing to 0. Take that limit. And it turns out we get something extremely simple as a result. Okay, so we can show that if we now make some assumptions. So our previous theory was extremely general. It was more general than cross-validation. We could apply it to things like bootstrap and jackknife and very general models. Now we're going to assume that we're just doing leave one out cross-validation. And we're going to assume generalized linear models because here we have to take advantage of sparsity, and that's sort of the right model for taking advantage of sparsity. So what's going to happen is we're going to run lasso. We're going to run our algorithm with the L1 penalty, and we're going to get at some smaller set of dimensions. Let's call them S hat. Now, just for the purposes of notation, nothing else, I'm just going to assume those S hat dimensions are the first dimension. Totally without loss of generality, just for notation. And what we see is that if we take this limit as the amount of smoothing goes to 0, that our new approximation is very simple. What you do is you first run lasso, you get your smaller set of dimensions, and then you apply our approximation on that set of dimensions, the much smaller set of dimensions. So that's it. And now we want to ask, is this approximation good in theory and experiments? Okay, so first, let's look at theory. So we can show that under assumptions that are familiar from the L1 penalty literature, that the time cost and the error of our approximation behave like the effective dimension, not the full dimension. So typically we think of this effective dimension as being much, much, much smaller, and the full dimension as being humongous, and so this seems much better. Now, if anybody's familiar with this literature, the assumptions can be a little hard to parse, and so we show that for things like linear and logistic regression, common GLMs, that with extremely high probability, and extremely high dimension, so a dimension that's almost exponential in the size of the number of data points, we can actually get this nice time cost and error dependence on the effective dimension rather than the dimension. Okay, and we see this in practice. So first, let's look at some simulated data that is a challenging number of dimensions, 40,000 dimensions. So here, what I'm showing you is, again, we're simulating a lot of different data sets, 25 data sets. That's on the x-axis. And we see percent error relative to exact CV on the y-axis. So, we're doing some kind of prediction, and we want to say, how does our prediction, if we used our approximation, compare to if we used exact CV? So what we have here in purple at the bottom is if we use that approximate smoothing. And so this is very bad. It's very biased. It's very far from zero. What we have in black is now something that you might have been thinking this whole time to yourself is, gosh, I don't have to do all of leave one out cross-validation. Why don't I just subsample some of the points instead of going to absolutely every point? And so what we do is we say, hey, we could subsample enough points so that our time cost is the same as if we ran our approximation, to make that as comparable as possible. And then the error is in black. That's an error that goes up to negative 40% and 20% in the other direction. That's not really a good error. The error of our approximation is in blue. You might have thought that that was the horizontal axis. It's actually the error in our approximation. It's not exactly zero. It goes between 0.06 and 0.04%, but it's pretty close. How about the time cost? So now we have the same lines that we did before. So our approximation is at the very bottom. It's, again, very close to zero in running time. By design, again, the exact subsampling method takes about the same amount of time. It's a little bit more. In this particular case, because it's so high dimensional, the smoothing approximation actually is worse than exact cross-validation, just because of that high dimensional matrix inverse, but exact cross-validation isn't great either. Okay, we look at a number of high dimensional real data sets, so things like breast cancer data, a news data, and a vision data set. If we use the smooth approximation, again, we see very large error, and our error is nearly zero in every case. And again, for timing, we see that the runtime of our method is much less than the smooth approximation, even though we're still getting these very good error bounds. Okay, so just to conclude, our approximation, the approximation that we've looked at today, requires just one algorithm run. Not n, not many, not n choose k as in the case of leave k out, just one. And then we use a Taylor approximation to be able to deal with the high dimensions. We do a Taylor approximation in this weighting scheme, this idea of an infinitesimal jackknife. We use L1 regularization as sort of a pre-processing step for dimensionality reduction. And the results we've seen are fast. They're automatic. You can just put in sort of any objective function, and this will just automatically work, again, subject to some restrictions on differentiability. And high quality, both theoretically and experimentally. So if you're interested in this work, I'll point out a couple of papers. So our first paper on the first approximation that I talked about today, the infinitesimal jackknife, it will appear in April in AI Stats 2019. It was awarded a full oral presentation. We call it a Swiss Army infinitesimal jackknife because you can use it in so many scenarios. And the second paper, approximate cross-validations for sparse generalized linear models. So this is the high dimensional case that we talked about just now. This was just submitted like literally about 24 hours ago, and so hopefully should appear on the archive shortly. Thank you.